because fluorine has a much greater positive center than lithium is, it's going to actually have a greater electron affinity. So it has greater chance of being able to get an electron. And when we happen to add an electron to fluorine, it actually releases energy. So I think about it as in, if you happen to have an affinity for something, it means you really like something. Maybe you really like pizza, or maybe you really like ice cream. And before, when you're not complete, you're needing something to fill yourself up, you're going to go after those things that you have more of an affinity for. And once you have them, then you release the energy and you kind of relax. You're a little bit more stable. It's kind of like being hangry. However, if for something like this, for lithium, it's going to take a lot more energy for us to add it on there because there's not really a great attractive force that's pulling it in. So it's almost like we have to have extra energy in order to get lithium to take that electron. You can think about it as if something that you have a low affinity for, like maybe Brussels sprouts, where somebody it's going to take a lot of energy to be able to get you to eat that versus something you like pizza. So this still goes back to this idea of nuclear charge and shielding. If you happen to have a lot of different energy levels, it's going to take energy because there's just not much of an attractive force there. So the positive is not spreading out super far to be able to actually take an electron from somewhere else and add it. So it's going to have to be a forced process to make this take an electron. In the same way, here when we're looking at these two, lithium and fluorine, because it's nice and tight and it's going to be smaller radius because of that attraction, then it's going to be easier for it to get an electron, and it actually releases energy, versus this needing to force energy, again, add energy to try and get lithium to take an electron because there's just not much holding it in place. So anytime we are looking at the metals, it's going to take energy to add an electron to a metal, and it's going to have release energy to add an electron to a nonmetal, which is why we generally see metals being positive, not getting electrons but having them removed, and nonmetals being negative because of those electrons being added. So with electron affinity, if we're adding this to our chart here, we might notice that it actually goes in the same direction as ionization energy. So electron affinity, the ones that are going to be over on this side of the periodic table, is going to have a much greater affinity for electrons, and the ones that happen to be towards the top will have a much greater affinity. Again, relating to the idea of attraction. So just which one, based on the atomic radius, has enough attractive force to actually bring those in, versus the ones that don't, and we have to kind of work hard to force them to take it. The last trend that we're going to be talking about is something called electronegativity. So when we're talking about electronegativity, it's actually an average of, I won't do it again. It's actually an average of our ionization energy and our electron affinity. Ionization energy is looking at how much energy do I have to put in to remove an electron from you. And electron affinity it's almost like how much energy is there that you are in order to pull that electron to you. So if there's not a lot of energy there when it comes to pulling that electron in, then we have to add that energy ourselves. However, if you're like fluorine and you do have that nice attractive force, then you actually release energy rather than having it added in. With electronegativity, since it is this balance, we are looking at the ability of something to be able to pull an electron. And I want to just make sure that we have this understanding straight. When we are looking at electronegativity, we're looking at it within a bond, so between two elements. And the best way to think about this is a tug of war. So if we happen to have one that is stronger than another one, then the one that's stronger is always going to be able to win those electrons. But if we have things that are fairly equally matched, then we don't have a clear winner. We don't have one that specifically takes it versus another one that's going to be losing it. So anytime we're talking about electronegativity, we're looking at an average of the amount of energy that it takes to remove something and also the amount of energy that is to add an electron to there. So for electronegativity, we're going to see, since it is an average of both electron affinity and ionization energy, it's going to follow the same pattern. So all you got to keep in mind really is that the one that is different is atomic radius, simply because bigger atomic radius, less energy is required to move that electron. When talking about electronegativity, so we're talking about that kind of like pull, the attraction, we're thinking about it as a tug of war between two elements. We've got a couple of different things that we can have happen. So if we happen to have a really big atomic radius, and we're going to have low ionization energy and low electron affinity, then we're also going to have a low electronegativity, which means that it's probably not strong. It's not strong enough to actually be able to take electrons, so this is going to give up electrons. If we're in the other situation where we happen to have a really small atomic radius and we have a big ionization energy, that means we're going to have big electron affinity. That means that we happen to have that element has a lot of strength with its ability to be able to pull electrons away from others. So this one's going to be the one that takes electrons. However, we can also have a situation where it's not a give and take. This happens, so this give and take happens when we have one that is clearly stronger than the other. However, we might have some that are almost equally matched, or one might be stronger but not strong enough to take everything. In this situation, the give and take, we're thinking about a bully who's strong enough to just come and steal your lunch. In the other situations, we're talking about a friend that you either split your lunch equally, or maybe they happen to eat, 3/4 of your lunch, but you still get to share it because you're still having that last quarter. So when we're talking about electronegativity, there is a range here. And if we happen to have an element on this side and an element on this side, then what we have in the center is where these electrons are going to be found. So let's say that we happen to have them, they don't really move much from the center. So they're in this little range here. And we're going to say that the difference between the strength of these two elements is 0.4. Now, if you're asking me what do I mean by the difference, you can take a look here in the top part of the periodic table and just look at your key. It might be in a different spot depending on which periodic table you have. But that top part tells us how strong each element is. So if there is 0.4 difference in between the strength of these elements, we're going to have something called nonpolar covalent. So that means that they're going to be sharing, they're covalent, so they're going to be sharing electrons, and they're nonpolar because no one has the electrons close enough to them for it to really affect their charge. We can also have a situation in which we have elements that are able to move it a little bit more, but they're not able to move it completely away. And in this situation, we would talk about that as being polar covalent. So if we happen to have, let's say element A is stronger than element B, and so the electrons end up over here much closer to element A than element B. Since these happen to exist in two different spaces, and this has the electrons closer, even though they haven't taken them, this one's going to be slightly negative because of the presence of those electrons. So we indicate that by using this little sigma sign, and we put it negative there if it's the one with the electrons. Over here, since element B lost the electrons, or they're further away from them, then this one's going to be slightly positive. So it's not as positive or as negative as if we actually had those electrons completely taken away, but because it happens to be found more in one area than the other, then it kind of affects the charge, just slightly though. Now anything beyond that 1.7 is going to be ionic. This means that the element was strong enough to completely take away those electrons, and now they own them for themselves. So one of them lost, one of them gained it. And so anything over a difference of 1.7 is going to give you an ionic compound. This is a much deeper understanding about how it is that we get these different compounds to form. So in the end, just to summarize, everything with reactivity is going to come down to this idea of attraction. And we want to make sure we use those terms, nuclear charge and shielding. Now, how attractive something's going to be is going to depend on the number of shells it has, first and foremost, And then, if those are equal, the number of protons. These ideas of attraction are going to determine how much energy we need to remove an electron, or how much energy we need in order to have something take an electron. And anything that is metal is going to be much more likely to give up its electrons because it doesn't have as much of a hold on them. Electronegativity is the average of these two concepts, and it talks about how strong something is to be able to pull that electron. And so if they're about the same strength, they're going to be nonpolar and not have a charge. If there's a little bit of a difference in strength, but not strong enough to be able to take electrons, then they're going to be polar covalent. And if we have one that clearly is strong enough to be able to take the electrons, then one's going to be ionic, and one's going to be negative, and one's going to be positive. Hopefully that helps go through some of the big concepts behind periodic trends, and just let me know if you've got any questions.